Hello students, welcome back. Today's lesson I believe is notes number 32 and the title is Concavity and Inflection Points. And this is a really important lesson. We have a lot of conceptual understanding in this lesson and particularly understanding graphs. And we've done a lot of work with derivatives clearly this year. It's been all about derivatives, but we've concentrated primarily on the first derivative of a function. And today we're going to involve the second derivative of a function quite a bit. In the past, we used second derivatives when we were talking about acceleration. So let's say you had a position function and then its derivative was the velocity and then its derivative was the acceleration. And so today we're going to talk a lot more about that second derivative. All right, so the first thing we need to know is what is concavity? Concavity describes the curvature of the graph. You can see my examples here. If you have something that looks kind of bowl shape, like you see over here, we call that concave up. Notice that you don't have to have the entire bowl shape, like you don't have to have the left and the right, you can just have part of it. And if it's curving up, like you're cupping your hand to hold something, then it's called concave up. Now let's take a look at the figure below where there is a curve that's concave up and it shows you some tangent lines drawn in. Now let's just put some numbers to those slopes. So let's say this particular tangent line has a slope of -1. Clearly it's negative because of the direction of the line. Let's say this tangent line has a slope of 0, and let's say this tangent line has a slope of 1. And if you went further, you'd have a steeper line, and maybe it has a slope of 2 and an even steeper line, and so on. So what's happening with those numbers? When you go from -1 to 0 to 1 to 2, those numbers are increasing. The slopes of the tangent lines are increasing. That means that f prime is increasing. So if f is concave up, f prime is increasing. Okay, if f prime is increasing, then its derivative is positive. So that means the second derivative, f double prime, is positive. So if your function is concave up, the second derivative is positive. Say that with me. If the function is concave up, the second derivative is positive. Say it again. If the function is concave up, the second derivative is positive. Key point there. Make sure you know that point. Now let's look at the figure on the right. So we have something that's concave down, so it's more of a mountain or a hill. You couldn't hold anything with it. It's downwardly curved, not upwardly curved. And again, you don't have to have the whole thing. You could have one or the other, still considered concave down. Now let's look at the figure on the bottom where we have some tangent lines drawn in. So let's imagine that this tangent line had a slope of 1, and then this one has a slope of 0, and this one has a slope of -1. So what we see happening with those slopes is that they are decreasing from 1 to 0 to -1, etc. So if the slopes are decreasing, that means f prime is decreasing. And if prime is decreasing, that means f double prime is negative. Okay, so if the function is concave down, the second derivative is negative. Say that with me. If the function is concave down, the second derivative is negative. One more time. If the function is concave down, the second derivative is negative. If the function is concave up, what's true? The second derivative is positive. And if the function is concave down, the second derivative is negative. Okay. Let's take a look at this example. We have function f of x. It's a cubic function, and you see I have the graph. And then we have its derivative. You can use your derivative rules and find that derivative yourself if you want to verify that. So the derivative of a cubic function will be quadratic, and we have its graph. And then we have the second derivative. So the derivative of the first derivative is the second derivative, and that one turns out to be linear, and we have its graph. Now let's take a look at what's happening. take a look at the graph of f of x, the original function. Do you notice where it is concave down? Do you notice that if I put this line in place right about here-ish, it changes from being concave down to being concave up? Do you notice that? Now, what's happening with the first derivative? At that point where the concavity changes, the first derivative has a minimum. And the first derivative is changing from being decreasing to being increasing. And what's happening with the second derivative? At that point where the concavity changed on the original function, the second derivative has a 0. And the second derivative changed from being negative to being positive. Okay? So, if you have a change in concavity, then your first derivative is going to change from decreasing to increasing or increasing to decreasing. And if you have a change in concavity, your second derivative could be 0 or not exist. We'll see examples of both. And your second derivative is changing from negative to positive or positive to negative. Hopefully this reminds you a little bit of the first derivative test where we talked about changes in sign. We're going to have something similar to that that has to do with concavity. Okay, what else do we want to notice about this? Well, I think what we want to do now is summarize all of this information in a table, and I hope that you will make this table and use it a lot and refer back to it as a reference. Normally I would give this to you as like a cardstock sheet and you would know that it's super important and that you would use it a lot. So, here's a whole table: graphical behavior, relationships between f, f prime, and f double prime. Let's say f is increasing. So let's just draw a sketch of something that's increasing. Could be like this. What do we know about the derivative? Well, the slopes of that increasing curve are positive, so we know the derivative is positive. What do we know about the second derivative? Actually, we don't know anything because it could be, as I drew it, it could be concave down, but it also could be increasing and concave up. So we don't know, so we'll just cross that box out. Let's draw a function that's decreasing. So it could be decreasing and concave up. We don't know. It could be decreasing and concave down. We don't know. But what we do know, if it's decreasing, is that its slopes are negative. So the first derivative is negative. And since we don't know about the second derivative, we'll cross out that box. Suppose something has a local maximum. F has a local maximum. It could be round and smooth. It could be pointy. If it's nice and round and smooth, we know that the derivative at that maximum is 0. But if it's pointy, then we know the derivative does not exist. So where there's a local maximum, the derivative equals 0 or does not exist. What's happening with the second derivative there? Well, if it's a nice smooth curvy one, then notice that the function is concave down. And if the function is concave down, what did we say was true about the second derivative? It's negative. So the second derivative will be negative at a local maximum, assuming it's a smooth curve, not a pointy straight one. How about a local minimum? If it's nice and smooth, then the derivative would exist at that minimum and the derivative would be 0. Or if it's pointy, then it could even be pointy like that. Then the derivative would not exist. What about the second derivative? Well, if we concentrate on the one that's smooth and curvy, like the first one, so these are both if it's smooth and if the derivative exists, not the extreme cases that aren't smooth and curvy. Look at the curve I drew under the f of x column. It's concave up. So the second derivative would be positive. I'll make that red just for fun. Okay. Moving along. If the graph is concave up, oh, okay, I think I wanted to say something a little bit different on the second derivative part before. Let me stop and think. I think we're okay. Okay, so if the graph is concave up, again, you could have something like this or something like this. It doesn't have to be the whole bowl, it can be half a bowl. What we know is that the derivative is increasing. And the second derivative is positive. If the graph is concave down, could be just part of it or the whole thing, we know the first derivative is decreasing and the second derivative is negative. Now we have a new term, inflection point. A point where the concavity changes is called an inflection point. So we should probably write that somewhere. Inflection point, or point of inflection. Is a point where the concavity changes. So you have a change from concave up to concave down, or a change from concave down to concave up. Now I have my own term for a point that you think might be an inflection point, you just haven't found out yet. I call that a potential inflection point. And I like to abbreviate that PIP, potential inflection point. That means you have some points, you think they might be inflection points, you just haven't found out for sure yet. It's kind of like critical points. You get your critical points, you think they might be maxes or mins, you just haven't found out for sure yet. Okay, back to the graph, chart. So an inflection point is a point where the concavity changes. So maybe it goes from concave down to concave up, or it could be the other way around, somewhere in there. We don't necessarily know anything about the first derivative at that point, but we do know that at that point, the second derivative equals 0 or does not exist. Because in order for concavity to change from positive to negative or negative to positive, you have to pass through 0 or have some kind of a break. Okay, so we want to refer back to this chart as often as necessary and try to get a grip on these concepts. And by the way, I'm not shortening this lesson really very much at all, just a tiny bit, but you're pretty much getting the full gist of this concept. Okay, the next thing we want to do is do some examples. And so what I'm going to do is end this video and start a new video, and video part 2 will contain all of the examples.